In this video, we look at a program or algorithm for depth-first search. As we have already seen that a depth-first search uses a stack. So if we write a recursive function, it automatically uses a stack. So for writing depth-first search, already I have taken a data structure for this graph. This graph is represented as a adjacency matrix. See, there are 7 vertices, so I have taken 8 indices, so 8 by 8, two-dimensional array. But this 0th row and 0th column, I am not using it. And then this is a visited array. All are zeros, means no vertex is visited. Then what is the procedure? This is depth first search. Suppose a vertex u is passed, means the starting vertex. Starting vertex can be anything, let us say 1. If the starting vertex is 1, then what I have to do? First of all, check whether that vertex is visited or not. If visited of that vertex is equal to 0, means it is not visited, then visited. So before visiting, print that vertex. Print %d vertex u. Print this one. This is printed. Then mark it as visited. See, assume that this is 1. Mark it as visited. Visited of u is 1. So mark this as 1. This is visited. Then start exploring it recursively. So for that, I need a for loop. So for v assign 1, v is less than or equal to n is the number of vertices, v plus plus. Then this for loop will go through all these elements in this first row. And every element we should check whether it is 0 or 1. If it is 1, then it's an edge. So here I will write down, if it is an edge in a vertex in a 2D array, that is matrix, at location u comma v, if it is equal to 1 means there is an edge, like u to v. Let us say v is a 2. So there is an edge. So perform depth first search on 2. So perform depth first search on 2. That is v. That's all. End of if, end of this one. So this will call itself again on vertex 2. Now this will be 2. And 2 is not visited, not visited. Print 2 and mark it as visited. Mark it as visited. Then scan through all the adjacent vertices of vertex 2. So now this is u. This is u because u is 2 now. So it will scan through this one. First one v, it's already visited. So nothing will happen. Next 0, it's not 1. So it will not call upon this. Then upon 3 it will call. So it will call upon 3 again. So this is how it will continue. To avoid the call, if it is already visited, I can add one more condition, that and visited of v is not equal to 0. Then only call. If it is already visited, it will not call the function. Anyway, if it calls also, this condition will stop it. Then how stack is used and all, I will show you. Then how recursion work, you know very well. You can trace this and check upon any small graph. This is a sufficient small graph. It's not too large or too small. So upon this graph, you can try this one and see how it is calling itself. That's all about a program on depth first search. We will see the demonstration for this one. In this video, we will develop functions for graph traversals, that is breadth first search and depth first search. I have an example graph. I will show that graph. See, this is a graph, a simple graph I have taken with 6 vertices and few edges only. We'll be performing breadth first search and depth first search on this graph. And I have already prepared a adjacency matrix for this graph. This is the adjacency matrix. Though I have only 6 vertices, I have taken a matrix of size 4 by 4 because there is no vertex with index 0. See, I am using this portion of See, I'm using only this portion of two-dimensional array. I'm not using zeroth row and zeroth column. So you can observe that zeroth row and zeroth column, they all have value zeros. So as when I did board work, I have started using vertices from 1 onwards. So that is the reason I'm skipping this vertex 0. Total 6 vertices, I have taken a matrix of order 7 by 7. Then for performing breadth first search, I require a queue data structure. So I have already taken a header file for queue, and this queue is using linked list. Already I have the functions like enqueue, dequeue as well as isEmpty functions. These are useful in performing breadth first search. Now let us write a function for breadth first search. Void breadth first search. It should take a matrix, that is G. First dimensions are not required. Second dimensions I have to pass, that is 7. And what is the starting point and what are the dimensions of a matrix, that is 7 by 7. Now inside this, what all the variables I require, I will be declaring them whenever I use. So first of all, I need a variable that is for start of a traversal. Then I need a queue, so I will say struct queue, I will declare a queue. And here on the top, I should include queue.h, that is the header file. Then here I need an array, that is visited array, of size 7, and this should be initialized with a 0, means none of the vertices so far visited. Then the first thing I should do is I should visit the starting vertex. So I will print that starting vertex. I have taken it in I. Then also I should mark visited of I as 1 to show that this already visited. And I should enqueue I. So I is enqueued. Now I should perform a repeating task by picking one vertex at a time and exploring it. So for that, while loop, while not is empty queue. So I don't have to pass a parameter queue. I don't have to pass a parameter queue because there's a queue using linked list. Now each time I will take out a vertex from a queue. So say dequeue, I'll get a vertex and I should start exploring it. So for exploration, I will take one more variable, that is j, that should start from 1, and as long as j is less than 7, that less than n and j plus plus, n is the dimensions. Then every time I should check if there is an edge and vertex is visited or not. So if g of I comma j is equals to 1, means there is an edge, and visited of j is still 0, means it is not yet visited, then I will print that to show that it is visited. So I should print j and I should mark visited of j as 1 because it's already visited now, and also I should enqueue j, and here I should declare one more variable, that is j. So this is a breadth first search function. Now upon this graph, let us call breadth first search from main function. Here I will call breadth first search, and I should pass g as a parameter, that is graph two-dimensional array, and the starting vertex I will give it as 1. Then the number of vertices are 7, that is dimensions are 7 actually. Number of vertices are 6, but dimensions are 7. Let us run this. Oh, there is an error. So where I have gone wrong? Okay. Struct queue is incompatible type. Let us check. Oh, yes. We are using a queue using linked list, so we don't have to declare or create anything. This is not a queue using array. Directly, this queue class is having front and rear pointer already declared, because for implementing a queue using linked list, we need just front and rear pointers. So I can directly start using the queue in the program. So I don't have to declare anything. So it's already there. So let us run it now. Yes, it is successful. Let us see the result. See, for breadth first search, I got the result as 1, 2, 3, 4, 5, 6. I will change the starting vertex. Starting vertex was 1, so I will say starting vertex is 4. Let us see what happens now. So for 4, 2, 3, 5, 6, then afterwards 1. How we got this result? Let us look at the graph. See, in the graph, when we are starting from 4, and 4 is explode, means the adjacent vertices are 2 and 3 and 4, 5 and 6. Yes. So 4, 2, 3, 5, 6. Then afterwards we can reach 1. So yes, it is correct. Now, if I give the starting vertex as 5, then I should get the answer like 4, then 2, 3, 6 and 1. First it should go on 4, then for 4, adjacent vertices are 2, 3, 6, then 1. So 5, 4, 2, 3, 6 and 1. Let us try with vertex 5. Yes, 5, 4, 2, 3, 6 and 1. Yes, perfect. If I give the starting vertex as 3, then for 3 it should be 1, 4, then 2, 5, 6. If I change it to 3, 1, 4, 2, sorry, 3, 1, 4, 2, 5, 6. Yes, perfect. So our breadth first search is working perfectly. Now let us write a function for depth first search. Depth first search is a recursive function. It should take a graph as a parameter. So the first parameter is empty and the second one is 7. Then I should give the starting vertex and also the dimensions. Now inside this we require a visited array. So I will declare it as a static type so that it is accessible in every call. So this is static size, it's 7, and I will make it as 0. So this is static array. Then every time we check that if that starting vertex is visited or not. If visited of starting vertex is equals to 0, means it is not yet visited, then we will check if there is an then we will print that one, print that vertex, that saying that it is visited. So I am giving the name as start only. Then we have to start exploring this vertex. So for that we will take a variable j. J starts from 1 onwards and j is less than n and j plus plus. And every time we check that if there is an edge from I, that is starting vertex, to j, if this is equal to 1, and also check that if it is not visited of j is still equal to 0, then we call depth first search recursively by passing array, and j will be the starting vertex and a number of vertices are n, that is the dimensions of a matrix are n. That's all. So it's a very simple program for depth first search because it is recursive. Let us call depth first search. Instead of breadth first search, we will call depth first search and we will call it upon first vertex. Starting vertex is 1. Oops, I did not declare a variable j, so I will declare a variable j. So I got an error. You can see that. See, I am showing you the errors so that if you type and you face any errors, you learn how to remove the errors. Yes, it is successful. Oh, it is printing so many values. So it has gone into infinite calling. So let us see what is the problem, where we have gone wrong. So it's not stopping at all. One thing we did is, after printing this one, after visiting a vertex, we should mark it as visited. We have not marked them as visited. That is the reason they are being explored again and again. Should be made as 1. So this part I missed it. So now it is marked as 1. So it will not be explored once again. So let us run it now. Yes, the result is 1, 2, 4, 3, 5, 6. How we got this result? Let us check it. Starting vertex was 1. 1, 2, 4. Then from 4, 3 and 5 and 6 are adjacent. So first 3, then 5, then 6. We are visiting, see, remember, we are exploring them in the same order, that is numerical order. So first 3 is visited, then 5, then 6, because 3 comes first, so 3 is smaller. So in the numerical order, they are being visited, though we can visit them in any order. So we can visit them in random order, first 5, then 3, then 6. So we can change the order, but we have to change the code. Now let us change the starting index. The starting index, let us make it as 4. So for 4, it will be 2, then 1, then 3, then 5, 6. 4, 2, 1, 3, 5, 6. If I give the starting index as 4, let us see what happens. Yes, 4, 2, 1, 3, 5, 6. It's perfect. So that's all. You can try this program and you can take your own graph and take some values. You can try it for directed graphs also. So draw the graph first and prepare a matrix, then write these functions and try them. This topic is about spanning trees. So in this video, I'll explain you what does it mean by spanning tree and what does it mean by minimum cost spanning tree. Then further, we have the topics like Prim's algorithm for finding minimum cost spanning tree and Kruskal's algorithm for finding minimum cost spanning tree. We will study this in next videos. So in this video, let us understand what is spanning tree. Spanning tree is a subgraph of a graph having all vertices of a graph. Like here I have 4 vertices, all 4 vertices, but n minus 1 edges, means the number of vertices minus 1 edges, so that there is no cycle formed by those edges and graph must be connected. So I'll define it formally. Like this is a graph, G is VE, G is equals to VE, and this is the number of vertices, we call it as N, and this is the number of edges, we call it as E. Now what is a spanning tree? Spanning tree, if I say S is the spanning tree, then it is a subgraph of a graph. We can find a spanning tree only if graph is connected. Then this spanning tree should have set of vertices and edges where number of vertices are same as number of this vertices and the number of edges should be equal to number of vertices minus 1. Number of vertices, total vertices minus 1. And there should not be any cycle. So this was all formal definitions. Now let us understand it in simple terms. So for this graph, I will show you what does it mean by spanning tree. This graph is having 4 vertices. So I must take all 4 vertices. Okay, 4 vertices are taken. Then, as there are 4 vertices, I should take only 3 edges. 1, 2, 3. Total there are 6 edges. I have taken only 3. This is a spanning tree. I'll take one more example. 1, 2, 3 and 4. I'll connect them like this. These 3 edges I have taken. Is it also a spanning tree? Yes. This is a spanning tree for this graph, and even this is also a spanning tree. So it means more than one spanning trees are possible. Yes, more than one spanning trees are possible. I will draw one more. 4 vertices I have taken. 3 edges. Yes, 1, 2, 3. Yes. Is it a spanning tree? No, it is having a cycle. It's not a spanning tree. And you can see that there is a vertex 3 which is not connected. So it should be connected and it should not have any cycle. Then we say it's a spanning tree. This is not a spanning tree. Then I'll draw a few more. See, these are also spanning trees. So various spanning trees are possible for a given graph. Can we calculate how many spanning trees are possible for a graph? Let us see. See how many vertices are there? 4 vertices. Then how many edges are there? 6 edges. Then for 4 vertices, how many edges must be there? Just 3 edges must be there. Means 4 minus 1. So from the set of edges, that is set of edges, I should select 4 minus 1 edges. So C V minus 1. That is 4 minus 1. So in how many ways I can select? That many spanning trees are possible. So out of 6 vertices, 3 vertices can be selected in how many ways? So 6C 3 ways. So for this example graph, it is 6C 3 ways. Yes, with this I can get the answer. But let us see something. If I take like this, without labels I am showing here, this is also 3 edges, but this is forming a cycle. This is also edges, but it's forming a cycle. 2 cycles from this one. If I take this 1, 2 and 3. So this is 1, 2 and 3. This is 1, 2 and 4. Then if I take this, this will also form a cycle. Yes. And even this will form a cycle. So 1, 2, 3, 4, 4 cycles are possible. I should not take those set of edges which are forming cycles. So total 4 I could find out, right? And there are 4 cycles in this one. And those cycles are formed by 3 edges, not more than 3 edges, because we are selecting maximum 3 edges. Whatever the number of edges we are selecting, we should see that a cycle is formed using those many edges or less number of edges also. So find out all those cycles, not more than 3 edges, and subtract that one. So minus cycles. So minus 4. 20 minus 4. So this gives 16 spanning trees. So yes, for this graph, 16 spanning trees are possible. So once again I repeat, how many edges we have, then how many edges we have to select. So they can be selected in 6C3 ways for as per our example. Minus how many cycles are formed by using 3 or less edges. So out of 3 edges we found there are 4 3 cycles possible. So that 4 I have subtracted and I got 16 different spanning trees. So if I generate all, I can generate 16 different spanning trees. I have taken only 4 here, right? This was not a spanning tree. Now next thing I will explain you what does it mean by minimum cost spanning tree. So for explaining minimum cost spanning tree, I have given weights to the edges of a graph. The weight for edge from 1 to 2 is 2 and 2 to 4 is 1. So I have given the weights. Now let us understand the problem. We want a spanning tree like these such that the cost of total spanning tree must be minimum. So cost means the total weights of all the edges that are included in that spanning tree. So already I have few spanning trees. Let us give those weights to this and check what is the cost. See, this edge cost is 2 and this is 5 and this is 3. So total cost is 10 for this spanning tree. And for this one, this is 5, this is 6 and 3. So this is 14. And for this, it is 5 and this edge is 4 and this edge is 6. So this is 15. Total cost is 15. So we are getting different cost, you can see. So till here, this looks like smallest. Then this one, 2. And this is 1, this edge is 1 and this is 3. So this is 6. Oh, this is more smaller. So I did not try all 16 spanning trees, just I have taken 4 and out of these 4 I got a minimum cost spanning tree as this one. So maybe this is the minimum cost or 12 more are possible. So I should try out all of them and select the best one, right? So that's the problem. We want a minimum cost spanning tree. So there are some algorithms like Prim's algorithm and Kruskal's algorithm for finding minimum cost spanning tree that we will learn in next videos. So that's all in this video. In this video, we will see Prim's algorithm for finding minimum cost spanning tree. So in the previous video already we have learned about spanning tree and the minimum cost spanning tree. So now let us see what does Prim has suggested for finding a minimum cost spanning tree. So for explanation, I have taken a weighted non-directed graph and it is connected graph. All the vertices are connected. So yes, we can find a spanning tree or minimum cost spanning tree. Now let us learn the procedure given by Prim's. So Prim's algorithm. Let us learn it step by step. So the very first step, Prim says that select a minimum cost edge from the graph. The minimum cost out of all these edges is 1, 6, 1 to 6. So first select that one. So this is selected. Now follow the steps very carefully. Next step is repeating step. So always we will be performing same thing. So let us see what is that repeating step. Now from the graph, select a minimum cost edge, next minimum cost edge, but it must be connected to already selected vertices. Selected vertices are 1 and 6. So it should be connected to those selected vertices. So if I look into the graph, the minimum one is this one. And next is this one, next is this one. No, don't say take those edges. Select the one which is connected. So for one, connected one is this one, which is of 25. And for sixth, connected one is this one, that is 18. So select this one, 18, that is 6 to 5. So next edge is 6 to 5, 18. Now repeat the same thing. Select the minimum but connected. So from 1 it is 25, from 5, 16, 12 and 11. So 12 is minimum. So select 12. Now next, from 1, 6, 5 and 4, find out the minimum connected. This is 25, this is 16. For this one, this is 11 and this is 10. So 10 is minimum. Take that minimum. This is 3 to 4 or 4 to 3, which is of weight 10. Now the selected vertices are 1, 6, 5, 4, 3. We have to select the minimum one which is connected to any one of these. So from 1 it is 25, this is 16 and this is 11, and from here 9 is there. So okay, select that as minimum. So 2 and it is 9, weight is 9. Then the next minimum is 2 to 7, that is connected to 2. Connected to 2. 6. Yes. So what is the total cost? 5 plus 18 plus 12 plus 10, 9 and 6, 60. So the total cost is 60. So this is a minimum cost spanning tree suggested by Prims. We have followed the algorithm and we got the minimum cost spanning tree. Now the question is why he said that it must be connected. See, we have to achieve two things. First is it must be a spanning tree. So tree will be connected and it will not have cycles. Yes. Second thing is we want minimum. So the first preference is it should be connected so that it's a tree. So if I look at the steps that I have performed, so first I selected this, then this one. Up to here if you see it's a tree only, connected only. The next connected. So if you stop in between also, if you perform few steps and stop, if you don't complete, still you get a tree only. So that is the reason Prim has suggested focus on tree, try to maintain it as a tree, right? Then check for a minimum edge. So this is how Prim's algorithm works. Now let us do some analysis on Prim's algorithm. How much time it is taking? See, what is the work we are doing here? We are generating n-1 edges and forming a spanning tree. We are scanning through and selecting n-1 edges. So this is definitely v-1. This is v-1, n-1. So n-1 edges we are selecting. And every time we are checking the connected one and finding minimum out of the connected edges. So how much time it will take for finding the minimum edge? So let us say maximum we are checking all edges and from there we are selecting minimum connected edges. So the number of edges are E. So the time taken by Prim's algorithm is V into E. V is number of vertices and E is number of edges. This is also linear, this is also linear. So we can say this is n into n, that is n square. So we can say this one n into n, n square. So the time taken by Prim's algorithm is n square. Then if you are using some heap data structure for finding minimum edge from the set of edges, then the time can be reduced to number of vertices minus 1 into log e edges. So if you see, this is linear n and this is logarithmic, so we can say log n. So the time complexity of Prim's algorithm will be n log n if a faster method is used for finding a minimum cost edge. Like we can use a heap or red black tree for finding minimum edge. Then one more thing about Prim's algorithm. See, if I have a graph which is not a connected graph, if it is not a connected graph, this is a non-connected graph. If I run Prim's algorithm on this one, then it will start from this minimum cost edge and it will try to select the next connected and next connected, so it will never reach on the second component because it is not connected. Yes, we already know that for a non-connected graph we cannot find a spanning tree at all. But what happens if I run Prim's algorithm on this one? So Prim's algorithm may find out a minimum cost spanning tree for one of the component. One of the component it can find out. Because they are not connected, it will never reach on the second component. So that's all. This is the analysis of Prim's algorithm. Next, we will look at a program on Prim's algorithm for finding minimum cost spanning tree. Let us write a program for Prim's algorithm. Already I have started a project. This is a C++ project I have taken. Here I have a hash defined for maximum integer. So you remember I have shown you that I is a constant, that is symbolic constant. I will use it as infinity. And this is a cost matrix, cost adjacency matrix of size 8 by 8. So 8 rows and 8 columns are there, where I am not using 0th row and 0th column. And the actual cost adjacency matrix is starting from 1, 1 onwards, right? From here onwards it's starting. So I am skipping zeros, that is 0th row and 0th column. Now next is near array that we have already seen on whiteboard, that it will find out the vertices are near to which connected vertex, means the vertices which are already in solution. So and the size is 8. Again here 0th one I will not be using, I will be using from 1 to 7. Then this is for the solution, that is T is for spanning tree, generating a spanning tree, 2 rows and 7 columns, that 6 will also be sufficient. I'll make it 6. Now here is a main function. In this I will write on Prim's algorithm. So first of all I will declare some variables that are required, that is I, j, k, 3 variables, and u and v are the vertices that I need, and also n, that is number of vertices. We have 7 vertices, and min, that is for finding the minimum every time. So I will take the value infinity. To find smaller value we need to have a larger value with us, so I is infinity. Now if any more variable required, I will come back here and declare them. Now let us start. The very first thing in the initial step of Prim's algorithm is to find the minimum cost edge from all these. So as I said, I will be taking the upper triangular part only and then find out the minimum one from there. So for that I will take 2 for loops for I assign 1 onwards, right? I is less than equal to n and I plus plus. This will scan through rows and this j will scan through column, but it should start from I onwards so that it can access only the upper triangular part. Then j plus plus. Then every time we will find out whether cost of an edge I comma j, if it is less than min, then we will change this min to cost of that edge I comma j. And also we will set u as I and v as j. So here we got an edge, right? The minimum cost edge we got. So with these 2 for loops, we'll be getting the minimum cost edge in the form of u comma v. So that has to be stored in a solution, that is spanning tree. T of 0 comma 0 assign u, and T of 1 first row and 0th column assign v. So we got this one. And also we have an array called that is near, and we have to update that array near. right? And before that, in the near array at location, that is u as well as v, I should set them as 0 because already we have included them in the solution. So these have to be declared as 0. I've made them, initialize them as 0. Now I have to update or initialize, I should say, near array. So for that I will use for loop for I assign 1 onwards, and I is less than equal to n and I plus plus. And in this one, I have to check all other vertices whether they are nearer to u or nearer to v. Right? Remember, we are doing the initial work. So if the cost of an edge from I to u, if this is less than cost of an edge from I to v, if this is small, first one is small, then we will set near of I as u. Otherwise, we will set near of I as v, near of I as v. So even if they are equal also, it will set as v, right? If u is less, then it will take u, otherwise it will set it as v. I'll remove these brackets. Now this is initialization of near array. Now we are ready. Now we have to include the rest of the edges. For this, the procedure is repeating. So for that, I will take a for loop, and for I starts from 1 onwards, because at the 0th location we already have an edge in the solution. So for that we have this I, and I should be less than n minus 1 edges will be taking. So this is I plus plus. Now we have to get remaining set of edges, that is n minus 1 edges. So 1 is already done. So remaining edges we have to take. So for this one, first of all, we'll find out from the near array which one is minimum. So we have to scan through this near array. So for that, I will take a loop starting with the j assign 1 onwards, because we are using near array from 1 onwards. So less than equal to n and j plus plus. So what we have to do here is we have to find out which one is minimum. So remember, before writing the condition, I should have minimum already having a infinity value, that is largest value with it. So set minimum to initialize minimum to I, then check here if cost of j comma near of j, right? You remember this code I have already explained you on whiteboard. I'm just typing the code and running the program to give you a demo. And that is less than min. If so, if at all, then we will set k assign j, and also we will change min to cost of that j comma near of j. These two things will do. So with this we'll get the k for which we have the minimum value. And one more thing, inside the condition we have to include only those whose near of j is not equal to 0, right? So this condition is also there. We should not come back to the same edge every time. The vertices which are already included, we should not consider them. So this is the condition, and checking the minimum one and finding the minimum one. So whichever is minimum, that will be set in k. Now once we are out of this for loop, that is j for loop, we got the answer, that is minimum one. So t of 0th row and ith column assign, we got an edge. So what is that edge? It's k, right? And t of first row then ith column is assigned with near of k, near of k. So we got an edge. And once this is done, we have to modify near of k and set it as 0. Means this vertex is already included. We are not going to use it again. Now we have to modify the near array. See, the first step is to find out the minimum one, that is nearest one, and select it, keep it into the solution. Then now update near array to check whether other vertices are nearer to k or not. So for that, again I have to run a for loop. So this for loop, again I will use j here, j assign 1 onwards, and j is less than or equal to n and j plus plus. And what we do here every time is check if, first of all, near of that j should not be equal to 0. Means the vertices which are already included, we should not consider them. And find out whether cost of j comma k is less than cost of j comma near of j. If so, then modify near of j as k, means this vertex is nearer to k. That's it. We should modify all these things. So once this is modified, then again the procedure will repeat. So this is the repetition for rest of the edges, and this is the code what we have seen on whiteboard. Now the remaining part is printing the solution. Now let us print the solution. So for this for loop, I can use I now because I am outside that outer loop. For I assign 0, I is less than n minus 1 edges, we will be having I plus plus, and just we have to print. So C out, I will print the values. First one is t of 0 of I, and second one is I will put the brackets here. I will put them inside the bracket. Okay, so this will put an opening bracket, then comma, this is the next thing, then after this second one. So as an edge I am showing it as an order pair, so t of 1 comma I. Then let us close the bracket. This is the closing bracket. The next is NL. That's all. So let us compile and see if there are any mistake. If there are any errors, I will remove the errors. Yeah, K is not initialized and used. Anyway, now let us run the program and see if there are anything left. If any mistakes, I will remove those errors. First, let us run the program. Yeah, this is the output. It is displaying 1 6, then again 1 6. Actually it should be 5 6, right? 5 6, then 4 5. Yeah, 5 6 is coming here, 4 5 is also coming here, then 3 4 is okay, then we have 7 2 2 2 3 also. So there is something missed here. Let us look at it. Condition, yeah, here I am checking the conditions. Near of j is not equal to 0. Yes, here also. Oh, here I have missed the condition. I have to write the condition here also. While initializing the array, I should say near of I is not equal to 0, then only check u or v. This is the first initialization of near array. So here I missed it, so I have written that condition now. So we know well that near of array should not be equal to 0. If it's 0 means we have already included the vertex, we don't have to include it again. Let us run it and check once again. Yes, this is the prems result that we have seen on the whiteboard, that is 1 to 6 and 5 to 6, then 4 to 5, then 3 to 4, then 2 to 3, then 7 to 2. Yes, this is perfect. So that's all. This is the prems algorithm. So you can type this program by yourself on your PC and you can test it. And it's easy. You can easily rewrite the code once you have done practice on it. And there is a PDF available after along with this video. Check for the resource. You will find a folder on the right hand side panel. So just click on it. You can find the PDF and you can download the PDF. So that's all. Try this program by yourself. The topic is disjoint subsets. This is useful for detecting cycles in the graph. So this is useful in Kruskal's algorithm. That is the reason I am covering the topic before Kruskal's algorithm. Let us understand what does it mean by disjoint subset. See, if you have a universal set, that is 1 2 3 4 5 6 2 10. I have taken an example. A universal set, collection of 10 elements are there. Now if I take that subset, I have two subsets here, A and B. Just look at the things what I am showing. Okay, A and B. If you check the numbers here, 3 5 9 4 7 8 10, if you take the intersection of these two, intersection is 5. So if you have subsets A and if you take intersection with subset B, then the result is 5. So disjoint subset means if you take the intersection, the result is, there is no common element among them. Now we use this for detecting cycles, so we need some data structure for representing. So how it is represented? We will see the data structure, that is the memory or array, as well as diagrammatic representation. So two things we have to focus on. So let us see. This is a universal set of 10 elements. I assume that every element is a set in itself. Itself is a set. So for each, there is a node drawn here. 10 nodes are there. And how to show that itself is a set? negative value shows it's a set. So we use this notation that negative number shows that it's a set or head of a set. For every number in an array, you find it's -1, right? So ignore 0 because I'm not using 0. We have the starting number 1 onward. So ignore this one. So all these are -1. It shows that each element is a set in itself. Like who is the head or parent of 1? Itself. 2, itself. 3, itself, and so on. Now let us come to the next thing. Now from here you can understand, right? Exact meaning you can get from here. Now I have set A and set B. Look at set A, 3, 5, 9. So this means that these three elements together are forming a set. So in this we have to select one of the element as a parent or head of that set. So we'll select one of the element. Out of this I have selected 3 as a head. And 5 and 9 are pointing on that one to show that that is parent, or it means we belong to a set where 3 is also present. That is the meaning. So 3, 5, 9, they belong to same set. Now here everything was -1. How we represent here? So I'll show it here. I have an empty array here, that same array. Now I have to show this set A. So for showing that, 5 and 9 are shown as children of 3. So at 5, I will write 3. And for 9 also, I will write it as 3. Then at 3, I have to write some negative value to show that this is a head or a parent of a set. So I will write -3. Minus is negative. Okay, what is this 3? This 3 means total elements in this one. Yes, there are 3 elements. Next, if you look at this set, 4, 7, 8, 9, there are total 4 elements, and I have selected 4 as a head, right? That number is 4, and the 7, 8, and 10 are pointing on to 4. So 4 is a parent or head. And 7, 9, 10 says that we belong to set 4. We belong to set 4. So 7, 8 and 10. Here I will write down 4, 4, 4. And at 4, I have to write some negative number like -1. So just writing -1 is not much useful. So we write the total number of nodes in this one. Now here total number of nodes are also 4. So I will write 4 here. This 4 doesn't mean this 4, right? This 4 means number of nodes. So total number of nodes are 4. So here 4 is written. This is how we represent sets in an array. So from that universal set, we have prepared one subset A, one subset B. So these elements are like 3, 3, 3. These are forming a subset that is A, and this 4 and the 7 and 8 and 10 are forming a set that is B. These are forming a set. What about the rest of the elements? They are not yet included. So let us put all of them as -1. These are -1. So that's all. This is the representation of disjoint subsets in a universal set. On this we perform two operations that are union and find. Union operation and find operation. Let us look at these operations. And union is also called as weighted union, and find is called as collapsing find. So I'll explain what does it mean. I'll remove this and show you. Let us say I want to perform A union B. Perform A union B. This is mathematical operation. Now if we perform union, the set of elements will be 3, 4, 5, 7, 8, 9 and 10. These two are combined together and there is nothing common, so nothing is discarded. Now how do you show diagrammatically? Diagrammatically I have to make any one as a parent, right? Only one as a parent, not both. So which one? Shall I make 3 as a parent for all or 4 as a parent for all? Whoever is having more elements, you select that one as parent. That's what weighted union. That's weighted union. So this is having more elements. So let us put 4 there. And 4 is already having 7 and 8 and 10. Then what about this 3? Along with its children, 3 will be pointing on this one. 3 will point on this. So this is 5 and this is 9. So all these nodes are joined together. They are together, they are connected, right? Under 4. These were independent, 2 different sets. There was nothing common. Now they are joined together, they became a single set. Now let us see how it is done inside the array. Actually the operation we perform inside an array. This is the diagrammatic representation. So what we do is, who is the parent of this set A? 3, 3. Right? Who is the parent of this set B? 4, 4. So this is 3 or 4, which is a smaller negative number, right? Negative numbers, this is minus 4 is smaller, means it is having more elements. Or if you take positive, who is greater? 4 is greater, so that is having more elements. So what we do is, the parent of this set will have 4 here. So this 3 says that my parent is 4. Then what about 5? 5 says that my parent is 3 and 3 says that my parent is 4. Now this was minus 3 and this is minus 4. Total it is minus 7. So we add all that together. This means that 4 is having total 7 nodes. Total 7 elements are there in that set 4. So if you watch here, 1, 2, 3, 4, 5, 6, 7 are there. Now if you check who is the parent of 4, 5, 5 parent is 3, 3's parent is 4. So the parent of 5 is 4, parent of 9 is 4, 10 is also 4, 8 is also 4, 7 is also 4. So this is how union is done. So I will write down a simple code for this one here for performing union. Union of head of a set, let us say U, and head of a set, that is V. Let us say head of a set is 3 and this is 4. Let us say I am performing union on this, that is 3 and 4. So for performing this one, I should check whose value is smaller. Actually it is negative, so I should check for smaller. If S of U is less than S of V, then who will become parent? S of U will become parent. But in S of U, we will write down the total value, that is minus 3 minus 4 we added and wrote here, right? So that is S of U plus S of V, and then we will change S of V's parent as now U. So we will make U as a parent if U is greater. Else S of V, we will add these two and write them S of U, U and V together, right? Then next is S of U will change to V. So that's what. See, this was having less number of elements, so 4 became parent. Otherwise, we can make it other way also. Like 3 will be parent and 4 comes under this, and under this we will have 7 and 8 and 10, right? And here we will have 2 that are 5 and 9. But we don't do like this, because who is having more element? 4 is having more element. Otherwise 3 will become parent if 3 is having more. So just how it looks like if 3 becomes parent, I have shown you. But this is correct, so this is wrong, right? We don't need this. Now back on this one. This is union operation. So as a C language function, we can implement this and we can say it is void union, it will perform union on this one. So one will be made as parent of another, and the total nodes are stored in the parent. This is union operation. Now, one important thing. How to know that there is a cycle? See, suppose the vertices, let us say 5 and 10. 5 belong to which set? Parent is 4. 10 belong to which set? Parent is 4. Oh, they already are in a single set. If you join them, it will form a cycle. If there is an edge from 5 to 10 and if you are joining, it will form a cycle. That's how it is useful. The purpose of making sets is, see, if you take in this case, find 5, 3, find 10, 4, they are in different sets. We can connect them, the edge 5 to 10. If they belong to same set, don't connect 5 and 10. It will form a cycle. That's it. This is so simple thing. To detect whether there is a cycle or not, this is used. So I have already explained you union. Now let us see find. What is this find? Find means we want to find out who is the parent of any node. Parent of 5. So 5's parent is 3, 3's parent is 4. So parent of 5 is 4. Parent of 9. 9 is 3, 3 is 4. Parent of 9 is 4. So find out the parent, that is topmost node, root node. So from here if you see, 9 says 3, 3 says 4, 4 says minus 7 means 4 is the parent. Minus, negative, so it's a parent. So this is find operation. Find 10. 10 says what? If you check 10 says 4, come to 4. This is negative, so 4 is a parent. So find operation means finding out who is a parent. Alright? So let us see this operation, how to find. For find I have written a function here. Find u. It means find 9, suppose. So the result should be 4 to show that 9 belongs to a set whose leader or parent is 4. So how to check it in an array? Go to 9, take the value here, s of 9. Go to 9, take s of 9. And go to 3, take s of 3. Go to 4, take s of 4. And if it is negative, stop and take this one. Don't take the value, take this one. That's it. So we have to go on taking the value of s until we get a negative number, right? As long as we are getting a positive number, continue. So for that, I have already taken a variable x and I have assigned that u. Now with the help of x, I will do. So this can be done using while loop. While s of x is greater than 0, means positive. What to do? Inside x, assign the value s of x. That's it. Simple. So if you trace this now, if I say find 9, then x is 9, right? S of 9 is greater than 0? Yes, 3. Then x assign s of x. S of x is what? 3. So x becomes 3. Now next time x becomes 3. So s of 3, is it greater than 0? Yes, it is 4. Then s of 3 is what? 4. So this x becomes what? 4. Then s of 4, is it greater than 0? S of 4? No, it will stop. So what is the value of x now? It is 4. That's all. That's the result. So it means to find the parent of any element, just we have to follow the hierarchy and reach till the negative number in an array. This is simplest. So we got the parent now. Just return x. That's it. This is what find is. So we will find out the parent. Alright. This is a simple function. This is a simple function. Now there is one more idea in this one, that is collapsing find. We will try to directly connect to the vertex to the parent directly. So you can find out, explore it by yourself. I have explained you the sufficient required things, that is union and find operation upon set, that are useful in our next algorithm, that is Kruskal's algorithm. So there I will not be explaining you union and find, I will be using them. So that's all in this video. There is a demo also available on this one. Let us look at the demo for Kruskal's algorithm for finding minimum cost spanning tree. For writing Kruskal's algorithm, already I have written few things here. See, the first thing is set of edges. This is already shown on whiteboard. Set of edges are there. 3 rows and 9 columns, because there are total 9 edges in our example graph, the graph which I have shown on whiteboard. If you have not seen that video, I suggest you go back and watch that video. Then this is the demonstration of that video. Here is first is the row of first vertex, then row of second vertex, then this is the row of cost of the edges. Total 9 edges are there. Then as we are using disjoint subset, so for that there is an array of size 8 here, because there are 7 vertices. So 0 to 7, that is 1 to 7 I'll be using. 0th one is not used. Then included, whether an edge is included in the solution or not. So for that we are maintaining an array, and that is all initialized to 0. Whenever we are including an edge, we are going to make it as 1. Then this is t of 2, 6 is an solution, that is spanning tree will be storing in this one, that is 2 rows and 6 columns, that is 0 to 5. Then for performing set operations, we have join, that is union, I should call it as union. And next is find, union and find operation. This we have already discussed, so I will call it as my union. Okay, my union, and that is u and v, it will perform union. This is a weighted union. And I was discussing about the collapsing find. This is the find, this is the code which I have shown on whiteboard, and this is the extra thing. I said that once you found the parent of any vertex, you can directly connect to it. So this is the code for connecting all those vertices directly to the parent that is coming along the path. So this is the extra code, and this is called as collapsing find. Now next, we have everything already. I have shown you these things, discussed these things. My union is there, and find and edges and set everything. Now let us write on the main function, that is the algorithm for Kruskal. Algorithm for Kruskal's algorithm is very simple. So what all the variables I require, I will declare them I, j, k, and u as well as v, and minimum for, and that let us initialize minimum to I, that is infinity. as a maximum integer, I am taking it as infinity, so it is initialized to I. And also the number of vertices are 7, and the number of edges, we have number of edges that are 9 edges are there, so that is 9. E is 9. Now this comes inside one while loop, because there are no initialization part here. Everything is repeating step, so we have to write on entire thing in a loop, and for that I have to take total n minus 1 edges, so I is less than n minus 1 I will write on. So let us initialize I to 0 starting onwards. So I'll be getting n minus 1 edges, so inside this while loop we'll get all the edges. Now here we have to write on the logic. Now inside this outer loop, I have to find out a minimum cost edge. So for that I have to scan through the edges. So I will use j, and j starts from 0, j is less than e, that is number of edges, and j plus plus, this is j plus plus, and every time I have to find out a minimum cost edge. And the min I should initialize every time whenever I am selecting a minimum. So let us do it here. This is the right place for setting minimum value, that is minimum as infinity. Now inside this loop I will find out minimum if cost of an edge, so that is inside array, that is edges, and inside third row, so that is index 2, that is 0 is the first row, right, 1 is the second row, so 2 is the third row, and the column is j, whatever the j value we are scanning. If that is less than minimum, then let us take u also, that is for first vertex we will take it for the edge first vertex, and second vertex in u and v. So that is edges of that is first edge is first vertex is in 0, so 0 of j, and then v is inside edges of 1 of j, whatever the minimum that we are getting. And also we should record this one, whichever j we is giving minimum, let us record it in k, because once that edge is included, we are going to mark it as 1, means once we have considered it, whether it is included in the solution or not, we are going to mark it as 1. Now once we are outside this for loop, we have a minimum cost edge. Now the question is whether we should include it in the solution or not. So for that we have to check whether it is forming a cycle or not. So for that we will call a find function, find, that is set function, find u, as well as we will find out v, both the values will find out. And these values should not be equal. If they are equal, means they already belong to same set, so by including this edge it will form a cycle. So if they are not equal, then we will include in the solution. So the solution is a t, that is spanning tree, t of 0 of I assign u, and a t of 1 of I is assigned with v. As we have included this edge, then we should perform union on this one. So union, I have named it as my union. Okay, this is my union function, and in this I should find of u and find of v. I should join the parents, right? I should not join just the vertices, I should join their parents. So I have given find of u and find of v. This will perform union, and also we should move on to next I, because we have got one edge in the spanning tree. We got the result, right, inside the result. So one edge is included in the solution, so move to the next index for the next edge. Then at the end, outside this if, anyway this edge we have already completed, so included should be made as, included of k should be made as 1, right? So here one more thing I missed here, whatever the edge you are taking, it should be included of that one should be equal to 0, right? Then only consider that one, otherwise don't take that edge, means don't repeatedly take the same edges as minimum edge, otherwise it will be always be finding the same edge as minimum edge. So if included is 0, then only take it, and once it is done, once you have found it as minimum, then at the end you make it as 1. So this is the entire while loop. So this is the simplest code of Kruskal's algorithm. That's all. We will get all minimum cost edges included in the solution. Now once it is done, we have a solution with us, so let us traverse through this solution array and display all the edges, that is all the edges that are included in the spanning tree. So we have n-1 edges, so I will print all of them. So I will use cout here, and I will display them as order pair, that is t of 0 comma I, and comma, next is comma, then t of 1 comma I, then close the bracket, then after that and L in the new line. That's all. So that's all with this algorithm for Kruskal. Let us run it, and if there are any errors, I will remove them. If any logical or syntax errors, let us remove them. Here I got the error because set is a array that is declared after the function call. So let us change this one. I am copying this one, cut from here. I should declare it before the function calls because the set array is not visible for them. So I have declared the array in the beginning. Let us run it now. Okay, are there any more errors? Yes, semicolon is missing. Let us see. Yeah, successful. Yeah, 1 6 3 4 2 7 and 2 3 4 5 5 6. This is what the result we have seen on whiteboard. So the same result we got, and you can see the order in which the edges are included. First is 1 6, then 3 4, that is the next minimum 8. This cost of this edge is 5 and the cost of this edge is 8, and I guess this is 10 and this is 12 something. Okay, and this is 16 and then this is 20. So this is how all the edges are included in the solution. So we got the result. So that's all in this video. You can try this program by yourself. If you do it by yourself once, don't try to just for an examination. If you are preparing, just don't mug it up. Do it by yourself. And if there are any variations possible, you can do that. You can take a data structure in different forms. Right, I have taken this edges in the form of rows. You can take them in the form of columns, or you can use structures. There are many possibilities. Or in classes, you can make it as a class, edge as a class. So a lot of things you can do. So you can try this program and write the program by yourself. And there's a PDF available along with this video. So that's all in this video. This section is about graphs. So we'll learn various things about graphs. But in this video, we will have introduction to the terminology used in graphs. For introducing terminology, I have taken various example graphs. So through these graphs, let us know the terminology. See, a graph is defined as collection of vertices and edges. So yes, every graph, if you see, it is having vertices. These are vertices. The circle one, nodes are vertices, and the links are edges. The links are edges. So graph is defined as G is equals to VE, where V is set of vertices and E is set of edges. Let us start with the first example. Here is the first example. See, this is a directed graph. So if the edges are having direction, so then it is called as directed graph. There is an edge coming out from 1 and connecting to 4. So this is outgoing from 1 and incoming on 4. Outgoing from 4 and incoming on 3. So it is incident from 4 and incident on 3. In a directed graph, if there is an edge connecting the same vertex, then it is called as self loop. This is a self loop. And if there are pair of edges between same two vertices, like it is connecting from 4 to 3 and then there is an edge from 3 to 4, then such edges are called as parallel edges. The next thing, the number of edges connecting upon a vertex that are coming in is called as in degree, the number of edges connected. Like there is an edge coming from here, there is an edge coming from here. So in degree is 2. And if there is an edge going out, the number of edges that are going out are counted as out degree of a vertex. If there are two vertices connected by an edge, then they are called as adjacent vertices. So these are few terms we have learned from there. Now let us come to this graph. This graph is not having self loop and there are no parallel edges. So without self loop and without parallel edges, a graph is called as simple graph. Then next, let us look at this graph. There are no directed edges. These are non-directed edges or undirected edges. So it is called as non-directed or undirected graph. And in short, we can also call it as graph. Graph means undirected. Digraph means directed graph. Then in an undirected graph or non-directed graph, the number of edges connected to a vertex is called as a degree, just a degree. There is no in degree, out degree. It is just a degree. And if there is an edge from vertex 1 to 2, for example, there is an edge, then it is taken as in both the directions. So it is assumed as it is from 1 to 2 also and 2 to 1 also. but it is not a parallel edge, it's a non-directed edge. So it is counted either way, 1 to 2 as well as 2 to 1. Then coming to this graph, see here I have a graph of 7 vertices, and there are two pieces of this graph, there are two components. So this is non-connected graph, it's not connected. There are more than one pieces, more than one component, so they are not connected. This is non-connected graph. And if suppose I draw an edge and connect it, then now the graph has become connected. It is connected. But you can see that there are two components connected here. So we also call it as connected components. A graph is having connected components, more than one components which are connected. Then one more thing. In this graph, after having this edge, if I remove 6, vertex 6 along with the edges, then again it will get divided into two components. Same way, if I remove vertex 4 along with these edges, then again graph will get divided into multiple components. So if there are any vertices in a graph whose removal will split the graph into multiple components, such vertices are called as articulation points. This is an articulation point. So 4 is also an articulation point. 4 as well as 6, both are articulation points. Then in that same graph, if I add one more edge, now there are no articulation points. If I remove any vertex, then graph will not split into multiple components. It remains as a single component. So that is biconnected components we say. It means there may be components, but they are strongly connected, biconnected. Now you can see that it was earlier not connected. I have added one edge, so it's connected. One more edge, now it is stronger. It cannot be broken into components by removing one vertex. So it is biconnected components. So we can simply call it as connected graph or biconnected components also. Now next is this one. This is a directed graph. And in this directed graph, from any vertex you can start and you can reach on all other vertices. You can go to 2, or from there you can go to 5, or you can go to 4, then 3. If you start from 4, you can go to 2 also. From there you can reach 5, you can go to 3, and from there you can go to 1. So from every vertex we can reach all other vertices. It means there is a path between every pair of vertices, or from any starting vertex you can reach all other vertices. If directed graph is satisfying this property, then it is called as strongly connected graph. So strongly is the term used for directed graphs. So same way here, from one vertex we can reach all other vertices, so that's how it is connected. So in non-directed graph we just use the term connected, but here we say strongly connected. Suppose this edge was in this direction, then we cannot reach 5, but it is connected graph only. It is connected, but it is not strongly connected because we cannot reach on all vertices. From 1 if I start, I cannot go on 5. So when we have an edge like this, then it is strongly connected graph. The next thing we will learn about path. Path is set of all the vertices in between a pair of vertex. Like from 1 to 5, the path is 1 to 2, then 2 to 5. Now similarly here, path from 1 to 7 is you can go to 2, then 5, then 7. This is a path. This is the path, right? Or else I can go from 1 to 3, then 3 to 4, 4 to 2, 2 to 5, 5 to 6, then 7. Path can be of with less number of edges also, or more number of edges also. Shorter length path or longest path also possible. So path is set of vertices which are connecting a pair of vertices. The next term is cycle. If there is a path that is starting from some vertex and going around few set of vertices and again reaching back, then it is called as a cycle. Like from 1 to 2, 2 to 5, 5 to 4, then 4 to 3, then 3 to 1. 2, 5, 4, then 2. It's a cycle. And here also we have cycles. This is non-directed, but still we have cycle 1, 2, 4, 3, 1. So cycle is a circular path or a circuit, we can also say, that is starting from one vertex and ending at the same vertex. The next is this graph, directed acyclic graph, DAG, DAG. This is a directed graph and there are no cycles in this one. There are no cycles. If you start from any vertex, you cannot reach that same vertex in any way. You select any starting vertex. So that is directed acyclic graph. There is no cycle. And the last thing is This directed acyclic graph, we can arrange all the vertices linearly in a single line. Those vertices are arranged in a single line such that the edges are going only in forward direction. The edges are not coming back. If you can arrange the vertices such that the edges are going only in forward direction, then it is called as topological ordering of vertices. This is possible only in directed acyclic graph. So that's all. These are various things we were supposed to know about graphs. In coming videos, we'll learn more about graphs. See, graphs are very useful data structure. Many problems, various problems can be represented in the form of a graph. And if we can solve a graph, then we can solve a problem. So problems are converted into graph and solved. If you want to solve any challenge, then you can convert that challenge into form of a graph and find a solution in the graph. Then you find a solution for a problem. So graph is very useful data structure in problem solving. So let us learn more about graphs in coming videos. Let us look at the representation of a directed graph. Already we have seen it for non-directed graph. We follow the same method, that is adjacency matrix and adjacency list. So here I have a directed graph. Let us see how to represent that one using adjacency matrix. I have taken a matrix of size 4 by 4 because here the number of vertices are 4. Number of vertices are 4 and the number of edges are 5. 4 vertices and 5 edges. Depending on the number of vertices, we should take a square matrix of size 4 by 4. That is n cross n. Now each row or column represents a vertex. Like first row represents first vertex or first column also represents first vertex. Now just like for a non-directed graph, here also we have to mark value 1 wherever there is an edge. So let us quickly do that. 1 to 2 and 1 to 4, there are edges 1 to 2 and 1 to 4. Remaining are zeros. Then 2 to 3, there is only one edge. And 2 to 1, 2 to 2, 2 to 4, there are no edges. 3 to 1, there is an edge. 3 to 1, there is an edge. And remaining all are zeros. 4 to 3, there is an edge. Remaining are all zeros. That's all. This is the representation for a directed graph. In non-directed graph, when there is an edge from 1 to 2, we were counting it either way. 1 to 2 as well as 2 to 1. But here, as it is having direction, just we will take it as 1 to 2. Now next let us look at adjacency list representation. For adjacency list, here is an array of linked lists that already we have seen in non-directed graph. Each location in an array is representing a vertex there. Then whoever are the adjacent vertices, we should have the adjacency list. So for 1, who are adjacent, 2 and 4. So these are the list of vertices who are adjacent. So this is adjacency list. Then for 2, there is only one vertex, that is 3. And for 3, there is only one vertex, that is 1. And for 4, there is only one vertex, that is 3. That's all. This is adjacency list. Then one more thing to observe here. See, I want to know what are the edges going out from vertex 1. From vertex 1, the edges going out are 1 to 2 and 1 to 4. Yes, 1 to 2 and 1 to 4. Then I want to know what are the edges that are coming in on vertex 4. So check the column. Yes, there is an edge coming in from 3 to 1. 3 to 1. Check the column. So 3 to 1, there is one edge coming from 3 to 1. So it's coming in. So I can know in degree of vertex 1 by taking column, out degree of vertex 1 by taking number of ones in a row. Like there are 2 ones, so out degree is 2. But in adjacency list, we only have out degree. But for in degree of vertex 1, I should search all linked lists and find out wherever 1 is occurring. So I found 1 time. So in degree is 1. I want to know in degree of 3. 3, yes, 1 time, like 2 time. So in degree of 3 is 2. So I have to check all linked list. But for out degree of vertex 1, just count the number of nodes in its own linked list. For this, 2 nodes are there. So the length of the linked list is 2. So out degree is 2. In degree we cannot know. Suppose knowing in degree is also important for us, then we can have one more type of adjacency list, that is called as inverse adjacency list. So I'll draw it here. So for inverse adjacency list, the method is same. We will take array of linked list. Then Whatever the edges that are coming on vertex 1, we will draw them here. So the edge is coming from 3, and on 2 the edges are coming from 1, and upon 3 the edges are coming from 2 and 4. See, for 3 there are 2 and 4, so you can see that there are 2 edges coming in. Then for 4 there is an edge coming in from vertex 1. So this is inverse adjacency list. So this is showing going out edges, and these are edges that are coming in. So if that is the requirement of an application, then you can have inverse of adjacency list also, and also you can have actual adjacency list. So that's all about representation of directed graph. You can also prepare a compact list, but you can show outgoing edges, or else separate. You can have inverse compact list also, that you can do it by yourself. So already we have seen compact list on non-directed graph. It will be in a similar fashion. Then little bit of analysis. If a directed graph is represented in the form of a adjacency matrix, then total number of elements are n into n, that is n square. Any algorithm which is processing upon this data structure may have to go through all the elements of this matrix, at least to check whether there is a 0 or 1. So it has to process all the elements, so the time taken may be n square if it is processing all the elements once. So the minimum time we can say, that is n square, if adjacency matrix is used. And if any algorithm is using adjacency list, then the time taken for processing all this is number of vertices, n, that is v, and these are all edges. So e, that is small e. So this we can say both are n. For assumption, we can assume both are n, and we can say order of n, and this is order of n square. So if adjacency list data structure is used, then the time may be less, and if matrix is used, then the time may be more. So whenever we analyze any algorithms, we will analyze their time assuming that they are using adjacency list. So we assume that the time taken for accessing the data structure may be n. Actually, the graphs are analyzed based on set of vertices and set of edges. How much processing is done is represented in the set terms of vertices and edges, because there are two different lists, list of vertices and list of edges. So that's all with the analysis. In coming videos, we will see algorithms on graphs.